All right, we're going to do the work kinetic energy theorem here, but we're going to add in that little bit of rotational kinetic energy. So I have a 0.625 kilogram basketball with a radius of 0.12 meters, starts from rest at the top of a 2.2 meter high incline. How fast will it be rolling at the bottom? So I have it going from one point to another point. So that means I'm going to use the work kinetic energy theorem, and it's rolling. So let's go ahead and see how that all fits in here. So the first thing I notice is no one's pushing it, so there is no work in. I'm going to leave friction there for a second. I notice it's rotating and moving at the end, so there's kinetic energy at the end. It's completely at rest at the start. I'm going to have to choose a height, so down here I'm going to choose height 0. So UG2 is 0. It's at a height of 2.2 meters, they told me. All right, 2.2 meters. And there's no springs. Now, work done by friction's a tough one because in the order to get the basketball to roll, there needs to be friction. However, there is no work done by friction. Now, the reason for this is because there's no displacement. And you're like, well, it's going down. Displacement meaning there's no sliding. Okay, so since there is a force of friction, but there's no sliding between the surfaces, there's no displacement between those two surfaces, so there's no work done by friction. If you're wondering what that force of friction is doing, that force of friction is allowing all of that gravitational potential energy that we started with to be distributed to the rotational kinetic energy and the linear kinetic energy, the translational kinetic energy. All right, so let's kind of move this down a little bit. So final kinetic energy, so 1/2 mv squared, it's moving and it's rotating. 1/2 I omega squared, and then minus mgh. All right, so this is how we address these ones. So it did tell me it's a basketball. So because it's a basketball, I will have to figure out what its I value is. And so for a basketball, it is 2/5 mr squared. I got that value from the table, and a basketball is a thin-shelled hollow sphere, and that's 2/5 mr squared. So I know my I value. Now I have V and omega in here. Now because it's rolling, okay, rolling without slipping to be specific, that's telling me that V is equal to omega times R. And R is the radius it's rolling on. So in this case, it's actually rolling on its radius, so it's a capital R. And what we're always going to do, and I hesitate to say always there, but I will say it, always, we're always going to substitute in for omega. And so let's see why we're going to want to do that here. So now I have, let's move the mgh over. So I have mgh is equal to 1/2 mv squared plus 1/2 I, which we're going to substitute in our 2/5 mr squared, times omega squared. So that's just going to be v squared over r squared. And so hopefully at this point you're seeing why do we substitute in for omega? Because we see that r squareds cancel. Nice. Also, we'll see now that we've substituted in for the I, the m's all cancel for us. So what's kind of cool here is that it doesn't matter the mass of this basketball. It doesn't matter the radius of the basketball. All it matters is how is that mass distributed. So is it a solid sphere, a thin-walled hollow sphere? What is it? That's the main factor. That 2/5 is the only thing that's left over from our I, is what is that fraction? How is that mass distributed? We'll cross out a couple more things here. I have a 2 on top and the bottom here, so we'll get rid of that. And so now we're left with GH is equal to 1/2 V squared plus 1/5 V squared. Take you back to 4th, 5th grade, adding fractions. So a half plus a fifth gives me 7/10. So I have 7/10 V squared over here. And so the last step is I need to solve for V. And so V is going to be the square root of 10 times 9.8 times the height, which was 2.2, divided by 7. Go ahead, plug that in your calculator. You should get 5.55 meters per second. And so that's how we introduce this rotation into the kinetic energy. We just have to account for it when we plug in our kinetic energy. That does it have both parts? Does it only have one part? So we do end up sometimes saying, oh, it's only moving, it's not rotating, so we'd cross this out. And that's pretty much what we did that whole start of the year when we did energy. So just a couple chapters ago, is we crossed that whole term out. We just ignored it. But now that we got things rotating, we have to account for that term, and so now it's in our equations.